Good morning, everybody. I hope you can hear me and that you can see the first slide of my presentation. I'd like to welcome you also to this series of webinars organized by Multibank Rekatama Patria. And I have the great pleasure to conduct these webinars. And this first one is going to be an introduction to soil behavior and index properties. So it's the first in a series. So in this particular webinar, we're going to look at soils, their origins, and some of the basic index tests that we use to classify them. And this, of course, is going to help us to understand their basic properties and behavior as engineering materials, in particular as fills. We work in an area of reinforced soil structures, so we're always interested in the properties of the fill materials that we use. And there will be later webinars looking at other aspects of the engineering and mechanical behavior of soils as well. This is an outline of the webinars we plan. We're currently February, and that's the one today. And then I have some further titles there. That might change slightly as we go through these, but we will mention the second one a little bit later on when we finish this first webinar. So soils. Soils are incredibly varied materials. So we see some interesting pictures here. A sand dune, an expansive soil, peat, a river gravel, you can see rounded, and a microscopic view of clay minerals. I think what you can see from those 5 pictures is that soils are very varied. So understanding their properties and using them as engineering materials requires that we do have a very good level of understanding of how these materials work. I'm just going to put a timer on so that I know where we have got to. So who should be listening to this webinar? Well, first of all, I should say I'm not trying to teach soil mechanics. What I'm trying to do is to just provide some basic information, and I want to illustrate it with examples from real soils and real experience. If you like, it's some of the lessons that I've learned over many years, which I think are important. There'll be a mixture of some simple explanations and also some more advanced concepts. Please look out for these little blue boxes. The idea of these blue boxes like this is that they will either add some extra information or maybe pose a question, and maybe that question could be part of the quiz later on. And this is aimed at civil engineers who have involvement in ground engineering, which, to be honest, should be most civil engineers. It might be useful or interesting to more experienced geotechnical engineers. And although I'm really concentrating on fills, especially fills to be used for reinforced soil, there's a lot of general geotechnical information presented as well. Some suggested reading. Well, in Indonesia, we're very lucky. There are 2 extremely good books which appear to have much the same title, both written by Dr. Laurie Wesley, who is a name that is well known here. The left-hand one is a fairly simple book, but the other one is rather more complex, goes into much more detail on the topic of soil mechanics, in this case for both alluvial and residual soils. Just so you can see what they look like, there is the simpler book. You can often find this available in the bookshops here. I tend to buy them when I see them because they're really inexpensive, and probably in some later webinars we may well be offering some of these as prizes to the questions that we might pose to you. If you want something to go a bit further or something different, the well-known book by Bowles, I'm pretty sure that has been translated into Bahasa Indonesia in the past. But one book that I rediscovered recently was a very famous text, the Soil Mechanics and Engineering Practice by Tensar and Peck, but it's been updated in a 3rd edition by Professor Mesri, and I'd have to say there's a lot of very interesting and excellent information in that book if you're interested to find a text to study this subject in more detail. So the content today is something like this. There'll be an introduction, We'll look briefly at the origin of soils. We'll talk about things like stress history and earth pressure at rest. Then we'll talk about obtaining geotechnical data. After that, the composition, classification, and naming of soils. Then these important properties for clays, the Atterberg limits. We'll talk briefly about soil phase relationships, and then a couple of words at the end about permeability. I think this is going to take me a little bit over an hour, but then after that, as you know, there is Q&A, and you can add questions to the Q&A feature at the bottom of the view whenever you wish. And also there will be a bit of a quiz at the end, and the questions in the quiz will be based on the content of this webinar. So I hope you'll have a go at that. Nothing very, very difficult, but maybe quite interesting. Anyhow, if we want to understand about soil behavior, a really good place to start off is on the beach, and that actually is Kuta Beach in Bali. And I'm interested in the area of sand there where you see it's a little bit wet on the surface. And you can go walking or jogging down there, and I don't know if you've ever noticed something about it. So let's just have a look at this. So there is this sand with this film of water on the top, and down comes your foot. And when you first do that, two things. First of all, the area around your foot goes dry. In other words, the film of water disappears, and it feels hard. It's really interesting to try that out one day if you're walking down a beach in that particular location. And then when you lift your feet up, you'll see a little film of water left behind. So let's do it again, just to be quite sure. So down goes your foot. And then with any investigation, you've got to be a bit careful about your boundary conditions. And in this particular case, something went wrong. So that was a failure, that experiment. So one last try. So there is the beach again, the sand. Down goes our foot. It goes dry. We get a dry area around the foot. It feels very hard. But if we then wait just a few seconds, we start to feel the sand getting softer. And we wait a little bit longer and we slightly wriggle our foot, and our foot can simply disappear into the sand. It's a very major change in properties. And this was a successful experiment, but can you explain it? In fact, hidden away in that behavior are quite a few important principles of soil mechanics. And we'll certainly try during these webinars to talk about most of them. But it's not quite the end of the story, in fact. That was Kuta Beach. And if we travel to the east about 120 kilometers, we come to a very interesting beach on the island of Lombok, Tanjung Aan. And when you look at the beach, it looks much the same. We have the sea at the end, there's some swimmers, there's no surfers this time. But if you try walking down this beach, it's almost impossible, and you certainly couldn't jog down it. So there's another question. Why is that the case? So something else we need to explain. So let's have a look at the sand in detail. And here we are. So this is Tanjung Aan sand. That picture is about 45 millimeters across. And what we can see is that the sand consists of these perfectly spherical little balls, and they're all much the same size. In fact, it's what's called an oolitic sand, and they're quite rare and really extraordinary. But when we look at Kuta Beach, the sand looks like this. And if I zoom in a little bit to make it a bit easier to see, then when we look in detail, the sands are quite different. And we can see very clearly now those spherical oids or oolites, as they're called, from Tanjung Aan. But on Kuta Beach, we have a variety of mineral types, a variety of particle sizes, quite angular. They're slightly rounded by the action of the sea. And not surprisingly, we've seen that the performance of those two sands is really quite different. So looking in detail at soils to help understand these sorts of differences, an important part of soil mechanics. A few words on origins of soils. These are words that you will often hear. So let's be quite quick about this. You will be able to download a PDF copy of these presentation slides after this event. So you will have all of this information if you wish to have it. But there are normally 8 and I've got 2 slides. So on the first slide, we have 4 items there: residual, alluvial, colluvial, and glacial. Well, of interest here in Indonesia, it's the first 2, residual soils and alluvial soils. So let's spend a little time thinking about those two. Residual soils come from the weathering of rock or other soils. And one thing that's rather important about this is that they can be very variable depending on the degree of weathering. And also their particle size can also be very variable. It can vary from clay to boulder sizes. So these are soils that can have a lot of surprises in store for you as an engineer when you're using them. Alluvial soils have been created by transportation and deposition by water. And what this tends to mean is that they're quite well sorted. They're often a little bit rounded, like we saw just now on the beach. And therefore, their behavior is likely to be very different to residual soils. And that's indeed the case. So in Indonesia, two of the most important soil groups are residual and alluvial. The other two of some importance, but I won't read through anything on those today. The other group consists of aeolian, which are windblown, organic, volcanic, and evaporites. And it's the middle two of greatest interest here. Organic, principally decayed vegetation. And of course, the famous deposit there is peat. We saw that earlier on in a picture. And then volcanic, these are soils that are being ejected or created by ejection from volcanoes. And we see things like lahars, which are granular soils. And when they weather, they actually become residual soils, and they can produce some very unusual clay minerals, which we will also look at briefly as we go through this presentation. One other thing I think it's interesting to be aware about, especially when we look at the marine clays, all around the coastlines, or around many of the coastlines of Southeast Asia, for example, the north coast of Java, parts of Sumatra and elsewhere, we have these marine clays. Also, for example, if you're from Malaysia or Singapore, you'll be very familiar with the marine clays. And just a couple of minutes on these, because they are such important deposits and they affect many infrastructure developments, because they are all around the coastline where we have flat land near the coast where we might want to make developments. And one thing that's really important is the effect of sea level changes in the deposition of these clays. And the two main ones we normally think about are the upper and lower marine clays, which we find around the coast of Southeast Asia, and it's strongly related to sea level. Now, that graph you see there is a diagram of sea level over the last 900,000 years, and it's going up and down. And of course, the low parts are where we have a glaciation, and the high parts are where we have an interglacial, where we are at the moment. So to make it a bit clearer, let's just look at the very early part of that graph. And here it is. So we now have a vertical axis, which is the sea level relative to today, and we have thousands of years along the horizontal axis, and you can see that same shape. But what's important here is that, first of all, you can see that sea level has been much, much lower in the past than it is today. Even say about 18,000 years ago, it was 120 meters lower down. And of course, this affects deposition of marine clays. And in fact, the only possible times when they could have been deposited are indicated by the yellow and red bars, which you can see up at around about the sea level. So that is the point in time when they could have been deposited. What this also means is that the upper marine clay, indicated by the red line, when it was deposited, is very young. And I have this really very nice picture, which was taken from some sampling I was involved with in Singapore a long time ago, but it's a Delft continuous sample taken right through the marine clay deposit in Singapore. And it would be very similar if you did it here in Indonesia. So what we have down at the bottom there is about 120,000 years ago, and the sea level was high, so a marine clay could be deposited, and we call this one the lower marine clay. But at the top of it, what happened then between 10 and 100,000 years ago, the sea level dropped, and that became a land surface. And the reason why we see all that coloration is that we get oxidation going on from the effect of sun and weathering at the top of the deposit. And in fact, if you look at the very top, you see that dark brown color, that is an old topsoil. So that was an old land surface. And then we had the end of that glacial period. The sea level rose quite quickly, And then we got deposition of the upper marine clay. And that was deposited between 3,000 and 8,000 years before present. And you can see there how we have shells in the bottom, and then we have a more uniform looking material as we go further up. So this is a very nice calibration of what we see when we look at samples and so forth in the marine clay. And I think it's quite interesting to see that. One important point is that if you're standing on a site which is underlain by marine clay, like this one in Malaysia, and what you can be sure of is if that is currently above sea level, deposition ceased about 3,000 to 4,000 years ago. And that is quite an important thing to realize. So if we look in at detail of this, at the end part of this period, where we have thousands of years ago on the top, and we have relative sea level on the vertical axis, then the only possible deposition time for those clays could have been around about what was called the mid-Holocene high stand, when the sea level was higher than today. It's the only way you can have a marine clay deposited at a ground level which is higher than the sea level today. So one important point to ask, whenever you're looking at profiles of soft clays, which we often do in this part of the world, it's important really to understand whether or not they're marine clays, because then you'll have an indication of their likely properties. And an important question is, what's the ground level? Because if the ground level is more than about 2 or 3 meters, it's really not possible that they could be marine clays. They would have to be formed in some other depositional environment. So this is slightly associated, but there are some important terms that we often see in soil mechanics: normally consolidated and over-consolidated. And I thought it was worth spending a couple of minutes looking at this and seeing how it affects soils. So it's all to do with stress history. So let's imagine we have a site a long time ago, and we have a soil sample down the bottom there, the little blue square. And at that time, there's a certain depth of burial, H, and a certain water level. And from that, we can calculate the vertical effective stress. And because it's the maximum that this soil sample ever felt, we'll call it max, sigma dash max. Or we can call it the pre-consolidation pressure, which we'll come to in a minute. So time goes on, and through some geological process, the ground level drops. Material is eroded away until we get to today. And if this is the situation today, then the vertical stress on our sample has become smaller. And there's a rather important ratio between that maximum value in the past and today's value, which we call the over-consolidation ratio, which is simply the ratio of those two values. And this is a very important thing to know about when you look at soils, whether they're soft soils or other types of soil. This is something important to understand. Something else we'd like to know, especially if we're doing finite element calculations, is what's the horizontal stress? And the horizontal effective stress is related to the vertical one by what we call the earth pressure at rest. And we use a particular symbol K0, which is the ratio of the two. It's the ratio of the horizontal to the vertical effective stresses. And this K0 value is strongly related to the OCR, the overconsolidation ratio. And there are a number of ways you can measure PC- for soft clays. We can use the odometer, which we'll see in a minute. But this is not so easy for stiff clays. And I'm going to use here an example of the London clay. You might say, why London clay? Well, I studied in London. I think it's reasonable I should do that. So let's have a look at that. So this is a profile of the K0 value measured in London clay by a variety of techniques at a variety of locations around London. And you can see that K0 is very high. This means that the horizontal in situ stress is much higher than the vertical one, up to 3 times. And it's been measured in a number of ways, but what's important really are the values that we see. Now, what I can do, I can relate that to the OCR using an expression like that. There are many variants on this kind of expression. They are empirical in nature, but they still give us an idea. So I can then translate that into OCR, the overconsolidation ratio. And you can see that it's very high, up to 100 times at the top of a deposit of something like the London clay. So that's a heavily overconsolidated clay. But if we have a site where the current stress is the same as the maximum part stress, OCR is 1, and then we call the soil normally consolidated. So we can determine this quite nicely from odometer tests. And here I have a profile of the overconsolidation ratio for a Holocene marine clay. It's actually in Malaysia. And you can see there that the values, once you get below a desiccated crust, the values are very low. They're actually close to 1. And those are determined from looking at the results of odometer tests. And I can then transfer that to K0 using that same sort of expression. And you can see there the K0 value, again, once you get below about 2 meters, is around about 0.8. And this is very, very different to London clay. If I quickly jump back to the London clay profiles, just see how different they are. The scales on the upper axes will remain the same. Here we go. There's London clay, hugely different. And this probably is a very, very good clue as to why those two clays have significantly different properties. And we might have a question about that later on as well. You can also get overconsolidation taking place due to a rise in the water table level. Not huge effect, but it can happen. But one thing to be aware of is that this whole concept of normally consolidated and overconsolidated really only applies to alluvial soils and maybe glacial ones where you had the weight of a glacier on top of them. But in many of the other soil types, it doesn't really apply. And that's important to realize that, because sometimes people try to use this idea of overconsolidation ratios, say in residual soils, and it doesn't really work very well. So just a few summarizing words here. Stress history in soils is very important, especially if you're using finite elements to model them. And true normally consolidated soils are not often found. Most soft soils we see, like the marine clays, would be very lightly over-consolidated. We can find under-consolidated soils, and they're generally in things like river deltas, like the Mahakam Delta. The deposition going on there would be creating some under-consolidated soils. And it is also possible to find heavily over-consolidated soils near the ground surface, like London clay, and they're quite stiff. But this terminology can apply also to sands, although it doesn't have such a marked effect. And just to remind you that it is principally applying to the alluvial or sedimentary soils, this whole idea of overconsolidation ratios, and so on. I mentioned that already. Stress history, when you're doing FEA, finite element analysis, it's important to get that right in your foundation soils. A few words now about geotechnical site investigation. I'm not going to go into this in detail, but it's just a few words, and in later webinars, we'll have a look at a bit more detail in some techniques for doing site investigation. But the main target is to find the distribution of soils at your project site and the appropriate, or the soil properties appropriate to the structures you're designing. That is kind of important, because you can spend a lot of time and money testing soil properties, and then you find out they're not useful. So you need to make sure that what you're measuring is what you need to know for the particular project the structure you're going to design. Of course, we want to get the best possible results. We want to keep costs as low as possible, and we want to do it quickly, because no one wants to spend too long on site investigation. This can all be optimized, and some of the techniques we'll talk about in a later webinar will look into that. Of course, one quick source of data is to have a look at geological maps and other published information. This can be a very useful source of data, and there we can see part of the north coast of Java. And if you look at the legend on the right, you'll see mention of Holocene deposits and other ones. But probably what most of you will see is geotechnical reports. And I think really these webinars are aimed very much at engineers who receive geotechnical reports, and then they have to make use of that data in their project and in their designs. So there are normally two types of report. There are factual reports, and these give descriptions of soils and measured parameters, borehole logs, maybe the results of in situ and laboratory testing. And it seems to be the case, especially in the good old days of paper versions, that there was a target to make these as thick as possible. Therefore, one important skill is making a very good summary of the information in these factual reports. The second kind of report is an interpretive or engineering report. And here, what should be happening is that the author takes the factual data and gives you an interpretation of the important parameters, for example, like the undrained shear strength, C dash and phi dashed. They may give comments on stability of slopes and foundations or provide you with allowable bearing pressures. And also in these reports, you frequently have large tabulations of data. And the only point I want to make here is that if you're an interpreter, if you want to use this information, it helps greatly if you can summarize this into a small number of plotted profiles or similar graphs, because you can see everything so much more quickly. And that is something which we need to look at briefly. So to give you an idea, something like this. This is a very nice series of profiles of properties for a Holocene marine clay. There are 4 of them there: the Atterberg limits and water content, then undrained shear strength, pre-consolidation pressure, and compressibility. Now, this information could quite easily occupy 1,000 pages of a report. But in one slide, in this case, you can very quickly see what this site looks like, what the properties look like. And if you're designing, say, an embankment over that clay, you have all of the data you need to go ahead and do that. So the skill of doing this is important. With these days, we have wonderful programs like Excel, where it's fairly easy to put this information into those programs and derive that kind of result. Now let's move on a bit now and talk a bit more about soil parameters. And as I said, I'm particularly interested in reinforced fills. So I'm just mentioning them and showing you a picture there. So obviously, when we're designing any kind of earth structure, with or without soil reinforcement, the properties of the fill are going to dominate its behavior. So we need to understand them well. Therefore, it's important that we take adequate samples and we carry out appropriate testing. And that's what we'll start to look at now. Here's a nice sample of soil. It's actually a piece of weathered granite from a site in Malaysia. And it's made up of a number of different particles: mineral particles, rock particles, maybe clay minerals, maybe some organic material. So if we look inside it and we look at the particles, we're going to have some large ones and then some smaller ones and some even smaller ones and some very small ones. And a very nice way to summarize that data is to carry out what we call a sieve analysis, where we use sieves, which look like this. These are very nice clean ones because they're from a catalog. And we pass the soil through there to find out the arrangement of the different particle sizes. And if we're lucky, we have a thing called a sieve shaker to do it. Now, sieve shaking, or the sieves are used basically for the sands and gravels down to 0.06 millimeters. So, and the particle sizes give us the principal names of the soils. So we have here boulders, cobbles, gravel, sand, silt, and clay, and they're each determined by the range of particle size, which I don't need to read out there. But just to make a point that this is one particular system. There are other, you can find other systems. So for example, the very important boundary between the sands and silt, which is between the coarse and the fine soils, that can be different. You might find it in other areas, like at 0.075 of a millimeter, for example, in the US system, but it's not very different. We normally then subdivide, so we get coarse, medium, and fine in the gravel, sands, and silts. And in this particular system, again, it's easy to remember because it's all 2s and 6s. So if you remember that the top end of the sand range is 2 millimeters, that's something you can kind of see, really, then everything else follows from there, and it's quite easy to remember, if you need to, those various ranges. So if I add some data here from 3 samples, I've got a green sample, a brown sample, and a blue sample, I can arrange them in that way, and that's quite interesting. But far easier is to plot this on a special kind of diagram, which we call a particle size distribution curve, or a grading curve. And this is how I like to do it. So we have the particle size along the bottom on a logarithmic scale, and then the percentage passing the sieves is on the vertical scale. And one little point to make here is that when you have these graphs, it's really helpful to add the names along the top. So often I see these graphs without them, and then you have to kind of think a bit, oh, where is the difference between sand and gravel? But add the names, and then instantly you can see that the green the green soil is a uniform coarse gravel, the brown one is a well-graded sandy gravel, and the blue one is basically a fine sand with some medium particles. So easy to see when the names are placed there. One little warning that in some reports, you'll find these plotted the other way around, especially in US practice. It doesn't really matter. You just have to kind of think of them backwards, but it has the same effect. And here are some pictures of some coarse soils. So this is quite unusual to see undisturbed samples of sand. And you've got here some medium and coarse sands sampled actually in a site in the UK. But these were taken with a special kind of sampler, the same one as I used for the marine clay earlier on. And you can actually see what the sand looks like in an undisturbed form. Not easy to do that. So another terminology now, uniformly graded. We use that term when the particles all have much the same size, like we had on the beach in Lombok. This particular picture shows it's a railway ballast, which is a man-made aggregate. But if you have single-sized materials, they're not very good as fill materials. The other picture at the lower half of this slide is a well-graded soil, where we go from fine soils all the way up to coarse ones. And generally, well-graded soils are much better as fill materials. And then there's the angularity of the particles. Top picture, that's a crushed material. So the particles are extremely angular because they've been crushed by a machine. But the lower one we saw earlier on, that's a river gravel, and it's extremely rounded because the stones have been rolled along maybe for many, many kilometers by a river, and it makes them very rounded. And of course, a rounded particle, not so good as a fill, whereas an angular particle would be very good to be used as a fill material. So these are all important little details that help us make assessment of the usability of these sorts of materials. Now let's move to finer soils. So again, using that tabulation, I've got a green, brown, and blue soil again, and I've done it in numbers there, but let's look quickly at the particle size curve because it's much easier. And we can see now that we have a green one, which is mainly a sand with a bit of silt in it. And then the brown one is mainly silt with a little bit of clay in it. And the blue one is mainly clay with a little bit of silt in it. So that gives us the names which you can see there in the legend. So for the coarse soils, which we normally separate between fine soils and coarse soils, the coarse ones are the sands and gravels. And those ones we can investigate using the sieve analysis. But when we get down to the finer soils, we can also use a technique to measure their particle size. It's a bit more complicated and not such an easy test to do, but to be quite honest, I would have to say that if I had to make a choice between Atterberg limits and measuring the particle size of fine soils, I would use the Atterberg limits every time, because these Atterberg limits tell you a lot about the nature of the soil. And when you're looking at clay soils or potential clay fills, the first thing I like to find out is, what are the Atterberg limits? And these are very useful little properties to help us understand better how these soils are likely to behave. One thing to mention now is that the reason I have a dotted line there halfway along this particle size curve is that's at 0.425 millimeters, which is halfway through the sand sizes. The reason I mention that is that when you do Atterberg limits, you have to remove all particles greater than that. So there is some preparation required in many cases. So you could carry out an Atterberg limit test on the green soil, but you'd have to remove the coarser material first. That is something to be aware of later on, and I'll mention it again when we look at data. Clay fills, yes, perfectly acceptable. In many situations, of course, we're going to use clay fills for highway embankments and so on, often for reinforced soil structures as well. We need to be aware that, in particular, some clays can suffer a lot of volume change, say from wet seasons to dry seasons. So they can change their volume, which means that they will deform. And if this is a problem, then maybe they're not such a good one to use in some situations. So you need to be aware of that when we look at clay fills. This is actually the wonderful tanah merah that we have here in many parts of Indonesia. It's a clay fill derived from volcanic material. It has particularly good properties. We'll mention that again in a second. Any kind of presentation like this wouldn't be complete without a few pictures from an electron microscope to look at these things. So these are clay minerals. The clay minerals are a very special set of minerals. And what you can see straight away is, first of all, they're very small. So that is a scale bar there of 1 micron. That's 1/1000th of a millimeter. And they are very small. Now, there are 3 main clay minerals that we talk about: kaolinite, illite, and montmorillonite, which are sometimes called smectites. And generally, the particle sizes are getting bigger as you go from K to I to M. So with my little K, I, and M over there on the left, I put an arrow there to make a point that generally, as you go from the kaolinite through illite to montmorillonite, the engineering properties are becoming, I'd say, worse, more compressible, lower phi values. You get into the area of the swelling soils, especially with montmorillonite. So it's quite important, if you possibly can, to know about that. And to show you, back with our good old friend London clay, this is a distribution of the clay minerals in London clay. And you can see the blue color is smectite or montmorillonite. And this is why London clay actually is a rather difficult soil. And if you've ever had a house on London clay during a dry summer, you tend to get all sorts of problems because of desiccation and drying out of the London clay. So I know not so relevant to Indonesia, but relevant in general to soils. So understanding something about the clay mineralogy is helpful when we look at clays. So here we are. This is an Indonesian soil. This is somewhere near Surabaya. It's a very expansive soil. You can see that from the wide cracks on the surface during the dry season. And that can cause problems because it allows water to get deep into the soil. And you can see here how we have a very low angle slope failure going on. And that's been caused by the nature of these expansive soils. A few more electron micrographs, but there's some quite interesting ones here. This is the marine clay in Singapore, Kalang Formation. And we can see nicely there, again, we've got that bar to show you the scale, 4 microns along there. And you can see a variety of particles. So we can see lots of little platey particles in a kind of very variable arrangement. But we also see what I call a loaf of bread, the bit in the middle, where that was probably a larger particle that has been weathered and reduced to a series of clay plates. So the clay minerals end up being these plate-shaped, having this plate shape. However, we do find other kinds of small particle in the marine clay. Those little almost circular particles are actually what are called pyrites framboids. They're tiny. I don't think the content is that much within a marine clay, but obviously they would affect the behavior. So more that this is the marine clay from Jura. We saw information about its over consolidation just now. You can see it looks quite layered when we have a general view, but when we look a bit closely, we start to see some interesting things. And this is the case in many of the marine clays around Southeast Asia. We find diatoms. Now, diatoms are basically they're silicious fossil skeletons. So they're made of silica. Silica is the same as quartz, of course. And in this particular case, this clay had up to 60% content of silica, which is very strange for a clay. And this clay has a liquid limit of 120%. And when we did some effective stress testing, we found that the phi value was 30 degrees. Now, if I tell you that we have a marine clay with a liquid limit of 120 and the phi is 30 degrees, you first of all would say that can't be right. But it was correct, and it was correct because of this particular situation with a very high silica content. It's not the same in every marine clay. In this particular location, it was. So here's a little bit of kind of advice that when you see data that is unusual, definitely important to question it, investigate it. But sometimes you need to be ready for something that's unexpected. And this is certainly the case in this particular marine clay. Here's another clay mineral, and it's a very special one to parts of Indonesia. It's called halloysite. It's also a relative kaolinite, but it forms these tubular shapes. Now, a couple of things going on here. First of all, you can imagine that these tubes all locked together could give a pretty good strength behavior, and indeed they do, but also they can hold a lot of water. And that's actually the case. We have a special name for this clay around Indonesia. We call it tanah merah, or red soil. And in this particular soil, the phi dash can be quite a lot higher than 30 degrees. And we can use it for fills. We saw this earlier on in a photograph, and it can make extremely good fill. So that is a clay of volcanic origin, because when these volcanic materials weather down, they tend to form this type of clay mineral. Now, one way we look at these Atterberg limit results is to, or the clay minerals, is to measure the Atterberg limits. And the Atterberg limits, as I mentioned earlier on, they are carried out on the particles smaller than 0.425 millimeters. So if we have a graph like this, where the horizontal axis is the water content and the vertical one is the remolded strength of a soil, maybe you've got it in your hand, then if you have a low water content, it'll feel quite stiff, but you can still mold it. And that would be something close to the plastic limit. But as you add more and more water to your sample, it becomes softer and softer until it essentially becomes almost a liquid. And we call that the liquid limit. Of course, we have specific tests for doing that. I'm not going to tell you how the tests are done today, but the difference between the two, we call the plasticity index. Now, these are these very useful numbers that give us some indication of the likely behavior of these clays. Sometimes we call, I've shown there these values as WL and WP, but sometimes people call it PL and LL for short. It's up to you. They have the same meaning, but don't forget they are water contents, but they're water contents at a specific condition. But we never put percentage after them. We just say liquid limit of 100. We know that means 100% water content. Here are some examples. We have here the upper soil, which is a sludge and probably pretty close to its liquid limit. It actually flows. And the lower picture is a compacted tanah merah, where that would probably be very close to its plastic limit when it's just right to be compacted into a structure. The way we normally summarize these Atterberg limits is to plot them on what we call a plasticity chart, or a Casagrande chart, where we plot the plasticity index versus the liquid limit. And then we have this rather well-known line called the A line, which is the inclined line on the graph there. And I've shown here two test results actually from the United Kingdom, a glacial till and London clay. And the point about this graph is that if you plot above the A line, then the material is likely to be a clay. But if it plots below the A line, it's likely to be dominated by silt content. And that's why we have this terminology CL and HL, ML and MH, sorry, CL and HCH, ML and MH. And you often see that those names appended to soil descriptions, a CH soil, clay of high plasticity. And that tells us something about the likely behavior of the soil. There are some more complex systems than this one, where you have many categories, but I'll just show the simple one here. One other system which we can sometimes come across is the AASHTO classification system where we have things like A76, A75, and so on. And it's very close to that other scheme with the A line. So an A76 soil would generally be very similar to a CH soil from the other system. Here's the diagram showing you what the marine clay looks like. The marine clay is a clay, plots nicely above the A line with a few minor exceptions there. And here we have some interesting soils. These are all clays, and they're all residual soils, in fact. But what's important here is that they are not following the normal rules. And you can see there we have three clays. We have black cotton soils, which are essentially montmorillonite, or rich in montmorillonite. We have the red Tanamera clays, where we have a lot of this halloysite clay mineral. And we also have allophane clays, which is another interesting type of clay derived from volcanic material. The point is that the red clays and the allophane clays plot well below the A line, but they are clays. So the point here is that the derivation of these ideas has come principally from alluvial soils. And sometimes those distinctions don't apply very well to soils with other origins. So we need to be aware of that when we look at this data. So if you looked at that blue material and said, oh, that's a silt, in this particular case, you would definitely be wrong. By far the best way to plot this data in a profile is like this. You saw it earlier on, but I'll just show you in a bit more detail here. So we plot the Atterberg limits as a bar, a horizontal bar with plastic limit at one end and liquid limit at the other end. And then we plot the water content as a series of dots, which if you like, you can link together. But it gives you a very nice quick picture of the nature of this soil. And you can see here that at around about 6.5 meters, there's a very distinct change. And in fact, the soils become much stiffer. And one way we can actually put numbers on that relationship is by what's called the liquidity index, which is the ratio of the water content minus the plastic limit over the plasticity index. And essentially it's the distance that the water content plots either side of the liquid limit. And it's just a nice way to put that into a single number. There are some information, obviously, which you can work out for yourself. But here's an interesting question. You'll see there are 2 points there where we have a water content higher than liquid limit. Question, is this actually possible? And the answer is it most certainly can happen. And it often happens in very sensitive soils, but there could be another reason. And I just want to show you what the other reason can be. So here is some work that was done to look at Atterberg limits and the effect of preparation, because I mentioned earlier on how we have to remove coarse material from the samples, which means you end up with a slurry or almost a liquid with the remaining soil. So you've got to dry them out. And they can be dried out in a number of ways. Or if you're lucky and you can use the material in its natural state, then that's better. But you can see what happens, any particular sample, as you go from natural to air dried to oven dried, the Atterberg limit values are moving basically to the left and down the diagram. So you're going to get different results. So we can have any of those three methods of preparation and they can affect the results. They can have a major effect. These are residual soils, these particular examples, and this graph is showing the same behavior for alluvial soils. So one point I'd make here is that when you're looking at Atterberg limit data, it's very important to be aware of how they were prepared because it can affect the results very significantly. So I would like to see this. If I'm looking at a tabulation of Atterberg limit results, two things I'd like to know. What percentage of material passed the 0.425 micron sieve, and how was it prepared? Because this would help me interpret the results. Unfortunately, I'd have to say, unless you really hunt back through the original laboratory data, you don't normally find that. But of course, if you're specifying a site investigation, you can ask for that information to be provided. And I'd recommend that you do. So let's just look at the last little thing on Atterberg limits. Let's look at a couple of profiles, some real profiles, and we'll go back to our friend London clay. So there is a really nice profile of the Atterberg limits and natural water content of London clay. And you can see that the water content plots very close to the plastic limit. So it's down at the left end of each of those bars. And then, not surprisingly, we expect that soil to be quite stiff. If I now compare that to the actual profile we saw earlier on, but this is a Holocene marine clay from Malaysia, then you can see now that the water content is plotting right over by the liquid limit. So these are clearly these are two clays that are going to behave very differently, but they are both marine clays. And as it says at the top there, the difference is the London clay is extremely old and has a lot of stress history, whereas the Holocene Giroux upper marine clay is very young, and the stress history is quite simple. So this could be a possible question for you. We have a sample from a depth of 2 meters in both of those clays, and there's a water table or phreatic surface at 1 meter, and they both have C dash of 2 kilopascals and phi dash of 26 degrees. This is very possible, but the London clay has an undrained shear strength of 100 kilopascals, and the Giroux clay has an undrained shear strength of only 8 kilopascals. Can you explain that using soil mechanics? So this is a rather important thing, and again, there might be a hint there of one of our quiz questions to come a little bit later. We have soil classification systems where we take things like particle size and Atterberg limits and we classify them. I'm not going to spend any time on them. These are things you can find in soil mechanics books and other documents. I did mention earlier on the AASHTO classification system, which, although not a mainstream one for geotechnical engineers, because it's aimed at pavement and highway construction materials. Actually, I quite like the AASHTO classification system, but get to know them, be aware of them. If you never know what you're going to see in a report, and if someone says they've got an A75 soil, you shouldn't be surprised by that. You should realize, oh, that's from AASHTO and it's just below the A line. So don't be surprised by that. So be aware of the systems being used in your country or your location, or what's being used in particular reports that you are looking at. Last little thing to look at for a few minutes is a bit of, if you like, undergraduate soil mechanics, is to look at the soil phase relationships. But these remain incredibly important. And if we have a kind of a nice image through some soil there, where the brown particles are obviously the solid bits and the white is the void, then we have this very important parameter, the void ratio. And the void ratio is simply the volume of voids divided by the volume of solids. And for me, that's something I always want to know, especially when I'm looking at the more compressible and softer soils. I'd like to know the void ratio. In one number, it tells you a great deal about the soil. Of course, those voids might be full of water. And if they're completely full, we call them saturated soils. Now, when it comes to thinking about our fills and our engineering use of soils, then a saturated soil would not be very good as a fill material. It would be very difficult to handle and place. So no, we don't want our fills to be saturated. Much more likely, especially in a fill, is that we have little air bubbles or quite a lot of air in it, which are the little white bubbles now. And then we say that the soil is partially saturated, which will be the case in most fills. And that's a good thing. We want our fills to be partially saturated to improve the way they compact when we place them. The famous water content, simply the weight of water over the weight of the solids. I think we can all remember that. And then another one is the degree of saturation, which is simply a measure of the amount of air in a sample, and it's the volume of water divided by the total volume. So if it's 100%, it's saturated, and if it's 0, it's dry. And then the way we try to understand these, and again, very much undergraduate soil mechanics, but we have this nice little phase diagram where we divide our soil into air, water, and solids. And then by having a sample of some sort, we can measure the total volume and the total weight of the sample. We know that the weight of air is 0. So we can then find out the weight of the water by drying it out and finding out the difference between the weight of the total weight and the weight of the solids. Then the other thing that we will measure in a soil is what's called the specific gravity, which essentially is the density of the solid particles related to the density of water. So typical number, 2.6, 2.7, something like that. We know for most soils it's going to be in that order. So we can then take these relations and we can make these simple expressions. We know that the volume of solids, we can calculate that, taking into account specific gravity. The volume of the water is easy. And then we can find out the volume of air by doing that simple subtraction. So this gives us the components of a soil sample, and we can then derive other things from them. Now, you need to be aware that when we get soil data in our reports, we only basically get three things that are measured. We get the density or unit weight, depending on how it's expressed. We get the water content. Of course, we're always looking for that in our report. And we get the specific gravity. And everything else, like void ratio or porosity or whatever it is you want to know, degree of saturation, is going to be derived from those three using some of those clever relationships. Now, I want to show two of these to you. I'm not going to try to explain them. If you want to look at these, you can look at them later on when you get a copy of these slides. But let's have a quick look. Example one then is to find a relationship between density and what is called dry density. Dry density is not a real thing. It's an imaginary density where we imagine that the water is missing. And we tend to use that when we look at compaction testing. And by playing around with those various relationships, we find out that the dry density equals the bulk density divided by 1 plus the water content. Now, that's an expression that's worth remembering, especially because if you're looking to find unit weights of soils for your designs and you go to the compaction testing, those densities will be given as dry densities. So you need to convert them then into bulk densities. The second example is a bit more complicated to do, but it's not that difficult. It's to find a relationship between water content and the unit weight, taking into account the degree of saturation. And you can do that by playing around and doing a bit of algebra. And I'm not going to go through that, but you end up with that expression at the bottom there. And this is a really useful expression when you are checking test data in reports. So let me explain how. So you can plot a graph of that expression, and I've plotted it there for a specific gravity of 2.63, and then you can add data from reports onto that. In fact, when in my very early days as a very young engineer, I can remember having that plotted on a piece of graph paper beside me, and when I looked at reports, I would quickly just check to make sure that data seemed to be in the right place. Now, that blue data is all very well behaved. The right-hand dot's very close to fully saturated and the other one's not quite. You'd have to say, well, did they come from below the water table, those samples? Should they be fully saturated? So quite a useful thing to look at. Here are some typical bulk unit weights. In most fill soils, they're going to be in the upper teens or low 20s at the most. I think we know that, but there's some typical values for you to take into account. But just that warning again, if you're using compaction test data to find bulk unit weights for design, say of a slope, then please convert it into bulk density using the water content. But two examples of how this can help you. Say I plot my information and I get those 3 points well above the brown line. That's a bit suspicious. They can't really be up there. So maybe there's something not quite right with those samples. The water content is either far too high or the density is far too high, one of the two. So maybe you need to investigate those samples to see what was going on. In this particular case, let's just imagine that those samples all came from below the water table, and you're relying on those samples, say, to measure the undrained shear strength. Then you have a bit of a problem there because 3 of them have dried out. They have a lot of air in them, and therefore you have to be very suspicious that you wouldn't rely on too much on tests, say like an undrained shear strength test carried out on those 3 samples. And then the last thing I said I would mention would be a few words about soil permeability. No more than that at the moment, it's just a few words. But what I would like to do here is just to try and demystify the numbers, because permeability is given by a parameter K, and its units are meters per second or something like that, but it's a speed. It's a measurement of speed, and it's the speed at which the water can flow through the soil. And I've put 4 different soils down there, and also their K values: a uniform gravel, a beach sand, maybe from Kuta, a silt and a clay. And the numbers become incredibly small, to the extent that they're really rather difficult to see their meaning. When I tell you that clay has a permeability of 10 to the minus 10 meters per second, you might say, whoa, that's obviously very small. But I have a way of thinking about this which is a little bit easier. So take that away. And basically, it's the time for water to travel 1 meter through this soil, but under certain conditions. So if I take a tube of the soil 1 meter long, and I place another tube full of water at one end of it, so the water can travel through the horizontal tube, and I let the water travel like this and drop out at the end, then the numbers there, those times, 2 seconds, 17 minutes, and so on, that's how long it would take. And you can see that in the case of a clay, over 300 years to travel through that sample. Of course, what this means is that clays are effectively impermeable. And of course, these numbers become incredibly important when we start to look at any analysis to do with the time effects of consolidation and so on, using finite elements or whatever techniques you want to use. So understanding permeability and getting the right values is extremely important. But that's just another way of thinking about what those numbers mean. So just remember, clay, 1 meter thick, it takes about 300 years for the water to travel through it. So highly, highly impermeable. That's where I come to an end. I think I've gone just slightly over an hour, which I thought I would do. Just to remind you that we plan more of these webinars. And the next one in March will be on a topic which I feel quite strongly about, which is measuring soil shear strength using the shear box and looking at the do's and don'ts of that particular technique. So I'll dedicate a single webinar to that because I think it's so important, and that'll be the next one we do during March. So I would just like to thank you for listening. You've had a chance, I think, to put questions into the Q&A section of this. So I think what we're going to do now is to start to look and see if we have any of those questions, and I'll try to deal with as many as I possibly can in the time available.